set to do all the correction as well. But the thing you got to know how to set up the standardization tab and standardized temperature, force, and all this information in order for machine to do the calculation. So in some sense, you still have to know this concept. Otherwise, you might wonder how come, what's the meaning of a standard tab? You don't even know idea. So this is a very good training for you to continue reading. Okay, let's continue. So yesterday, that was yesterday, right? Yesterday we were talking about reading all this bit, right? And then the fastest way is like you do this bit. This one is 100 meters, right? 100 meter it's not in a standardized meters, so you convert this 100 meters into the standardized meters. So the standardized one might be because you can take a look. The standard one is 85 degree, and now you are using the mean one. Temperature is 63. So mean is shorter. You are using something shorter. So it means that you overestimate the real the standard in comparison to real. Well, in order you overestimate the real distance. So in this case, you have to deduct the correction bit from error, from the one. So the 100 will deduct some value. Deduct this one, CT. But now the whole CT, because this error corresponds to the whole every bit. You sum up every bit, it becomes 882. So this error indicates this one. But if you want to calculate individually, you got to calculate. Indeed, it's better to calculate individually because all the degree differs. You see, this degrees differs. So you better convert this 100 into standardized tab unit first, and then do the slope correction secondly, and then do every bit like this, then add up. Then you'll get the standardized corrected slope corrected AB distance. That's the basic idea. I mean, let me reiterate the idea. The idea is now we have two mistakes. I won't call it mistake, two errors. The two description probably is better. Two description over here. One is the slope. The slope we have to correct because you are going to calculate the A1, A2, and blah blah blah, so on and so forth, up to B, A power something B. Okay, so but the thing is this is the slope. You only can measure all these slopes. Or since you can only measure these slopes, but if the tab is already a standard one, then there is no problem. You can use 100 times cosine this degree, then you get the standardized units over here, meters or something over here, standardized one over here. But the thing is this 100 is not standardized one. This 100 is use the tab in hand is 63 Fahrenheit degree Fahrenheit over here, and so the length itself is shorter than the standard one. If you're using something shorter than the standard one, it means that you overestimate this one in comparison to a standard tab. You overestimate because your tab is shorter. So of course it turns out is a longer one in your tab, but in the standard one it's supposed to be shorter. So you have to deduct 100, deduct something. Something is called temperature correction. Deduct this one. But this error is supposed to be 100. Deduct this one 100 over here. You have to change this 100 over here because you have to correct this one into the under this temperature first. So after this correction, 100 minus CT. Of course, this error must be corrected as well. So after you do the correction, it might be 99 point something over here, and this one is the standardized tab measurement. And keep on doing all this bit. And then every bit, you can get a standardized one. And then the secondly, do the slope correction. Use the standardized measure times this one. Then you'll get the result. Okay, let me take one for example, because the author is written something is a bit hard to understand. Because he put error, it's supposed this error to be divide into L1, L2, something like this one. It's easy to understand because he sometimes writing something probably he understand, but it's hard to convey the information to others. So let me write something easier to understand. So take this one L1 out. I just calculate this one for you, and then you can do the other bit by yourself. Okay, I take this 100 out. Let me show this one for you. You can check my approach is the same. The result will the same. I just check my result will be the same like his like this one. You get this one 879.282. So by your tab use tab is this one 882.2. But there are two arrows in between. One is the slope arrow, the other is the temperature arrow. So you have to correct this one to the standardized one. The standardized one will be 879.282. Okay, so now I'm going to show you my approach how to get this 879.2.2 based on some much more intuitive approach, because writing something is really hard to understand why is writing this one. So if you can understand, it's fine, but for me, I don't see too much information out of this equation. So I use my approach. Take a look. So first off, I calculate the slope. The standard slope. Let me get rid of all this bit. It's a bit ugly, right? By the way, we almost half of our lecture already. So you have to be facing very soon with either essay or exam. Probably it's an essay because I don't know how to exam you online. Probably it's hard to do exam thing. Probably essay, but from essay I can easily understand whether you participate in the class or not. Because I have my own rotation and my approach, so I can easily tell whether you copy online or you really learn from this course. So if I don't trust you, then maybe you don't get high scores. Maybe okay. So I take the first one, for example, L1. This is it's not doesn't look like L1. This is L1. L1 is use tab. I use your tab. So this is the first segment. The first segment use your tab to do this measurement. And this one is 100. L1 is 100. And this is in your tab, right? So this one must be corrected first. So what I'm gonna do now is I correct this tab first. So I'm going to correct this tab to what? To this one. And by the way, there is maybe if you are acute, maybe you will raise one question as well. How come you only correct the distance rather than the angles? Why do you believe the angle is absolutely correct? We don't, but we cannot do everything all together. We have to do bit by bit. And also in this book, probably doesn't mention anything about correction the angles as well. Because once you use the machine, in some cases, you have to use some machine to measure this angle. Once you use the machine, you relate to the temperature as well. So this angle must also be corrected as well. So it's more than just two. Maybe to be more precise. It must be three to be corrected: slope, the temperature tab, and also the temperature angle. All these three factors. But now we omit this one. In this book, it seems like the author doesn't care about the angle, but to be precise, angle also has to be corrected as well. Maybe up to some point, he will mention this bit, but at least for this chapter, we can just skip this bit. This one for as the standard one. To this the slope, this one are the standard one. Indeed, they are not because they are not. But we take it as standard one. Okay, let's continue. Just to let you know. So I convert this one 100 into the standard one, standard tab. So this one will become standard tab like this one. One L1S. Let's say this L1S. Let me put this into the superscript over here. L1. L1 is the this one, the first segment. Okay. Now I have to do the correction. So L1 will be like this one. The temperature, just like say, I will be L1. minus the correction. And yesterday I assigned you, told you if you can sub the one, I gave you the equation and make it right, and then I give you 5 points. So far I haven't received anyone tell me. It's supposed to be quite very easy, but so far I haven't received anyone telling me his answer. Maybe you haven't thought about it. It's quite easy. So once you think it through, it's supposed to solve it very easy. So encourage you to solve it. Okay, so now it's L1, L2. So the one I gave it to you is if you want to make sure it's absolutely correct, it made a absolute value over here, then it's absolutely correct. Absolutely correct. Otherwise, you have to always take care about plus minus. I don't want to think about plus minus all the time. So I just give you an absolute value to just to save some fast. Okay, in this case, how I'm going to know this CT? Going to know this CT. So CT, yesterday I gave you guys the equation. I gave guys the equation. Let me show the equation again. The equation is let me see, it's over. Yeah, it is. Yeah, it's over here already. It's over here. But it's just this error is not this error. Because this error means the whole error. So this correction have some problem over here. Of course, it's correct everything. But the thing is that we have 1 second, the other second, 1 second by segment by segment. So it's better to correct bit by bit. So that's different from my approach from his. He correct everything all together. I prefer to correct 1 second by 1 second. It's easier to understand. So I correct this segment first. This 100 to be corrected. The reason because all the angles differs. So I don't intend to adopt this one. Otherwise, you have to how to explain this one. Okay, so CT is alpha is a thermal expansion coefficient. Is alpha. Alpha depends on your material. Depends on a lot of things. Material basically is the material used. It different response to the heat. Is a heat transfer. Okay, so and then the TM last time yesterday with say TM is a mean field value. You go outside to a field and the mean value, mean temperature. Mean temperature is this is called mean field temperature. The mean field temperature minus T naught. T naught is the standardized temperature. Standardized temperature. Standardized temperature is just a referred temperature. It could be any temperature you refer to. Here you refer to as 85 degree Fahrenheit. So this is 85 degree Fahrenheit. And then times L, here is L1. Because I take part all the pieces, take them into parts. I rather than put all them together. So for me, I put only L1. So I calculate this. I correct. Put this 100 into standardized one first. Let me do it over here. So alpha over here, I already give you alpha over here. The base is over here already give you. Yeah. And then look at the unit of the alpha. The unit of the alpha is 6.5 times 10 raised to minus 6 per Fahrenheit, per degree Fahrenheit. This is important, per degree Fahrenheit. So it related to the temperature. So this is 6.5 something, 6.5 something. So basically this related to, of course, you can check the unit of this one as well, 6.1 something unit, but we care more about the per unit over here, temperature here. Okay, let's continue. Okay, so if you substitute this one, this is supposed to 6.15 point over here. So this value will be here. So this value will be the same. I just put over here. Otherwise, I have to write a lot. And this value will be different because I don't put all of them together, something up. I don't. I just correct 100 first. So for me, this one is times 100 first. This one times 100 first. Okay, if you time 100, you can get a correction for this one, just for this bit. So minus this bit. Minus bit. And let me use the calculator faster. Maybe I can calculate this bit as well. Maybe get some calculator faster. Then we can. There are some online calculator. Let me see if I can get a get one here. I used to have some online calculator here, but I think it's gone now. Let me get another new one. You can also have some copy of your online calculator. Okay, so you can use some. This is not good one. I don't like this one. Because there's some is a better one. Either this one was this doesn't serve a purpose because I will have an exponential raised to exponential. So it's based scientific one. Online scientific. This one probably is this one, I think. Okay, this is the one I used to use. This online one, so I just make copy of it online. Okay, so now the 6.5 times 10 power of minus 6, then times what? Then times let me check, 100 or something. Then times 6.5, then times 63 minus. Anyway, minus 63 is also okay because we just put the absolute value on top to save all the files, so it doesn't matter as long as you remember something. Okay, so 100 0 point something minus 0.0143. So let me write down. Let me go back. If my correct, if my calculation is correct, then I supposed to have this value. So this value is to be minus 0.0 how much? 0.0143. Okay, so this one can be now LOS. You can get LOS. LOS now is easy. It's 100 minus the absolute value of 0 point something. That's the reason for me to use absolute value because I don't have to use my brain at all. I need plugin. Otherwise, I have to use my brain. So how much do I get? It's 99 point something. 99.9857. 95. Okay, so this is the standard one. Now, second approach. Second one is correct the slope. So you correct the LOS already. You correct 100 to the standard. Is you correct the slope. So the slope correction, and this slope is this angle is 2 degrees 20 seconds. Is 2 degrees 20 seconds. Okay, not second minute. Okay, so you are going to do this correction, and how are you going to correct it? Easy. You just this LOS 1 times cosine 2 degree 20 seconds, and you can convert the 2 degree 20 seconds to your radians in radians. So you can I don't know whether this calculator give you this kind of things. In sine, if that sine is 60 degree, is that possible? Degree. It seems like there is no degree. So you probably gotta use into a radians. Degree over here. That degree. There's a 30 degree. This a radian. So let me see. See, so it's 2 degree, and then how much? Then 20 seconds. So it's 2 point. How much is 2 point? Let's say 33 something. 2.33 degree. It basically you can convert to degree. The second can also convert to degree. So eventually times your 99 point how much? 99.9857. 985. Pretty much how much do you get? This one is 3.333 something to get it much more precise. Okay, so eventually how much do you get? How could it be this? I probably get, let me see. Cosine. This is cosine, not sine. How come I type sine? No wonder. So weird. This is sine. Cosine, not sine. Okay, so the result you get is 99.9027. So this is way in 9027. So eventually you get 99.9207. 9207. 9027. Okay, and so this is the final one. This is the final one. Just for L1, and then you do everything together. L1, then you do the same approach for L2, and adding up together, and then eventually you get this result. And then this approach is easy to understand. But for this author, really, it's hard to follow this error because it's doing error this. But then later on, of course, you have to separate all this bit. You can do the derivation, but I don't want to do a derivation for this bit as well. You can do the derivation to make sure it's correct. And we can just use our approach easy, a bit by a bit, and then put them together. It's easy to understand, and then add them up. That's the final solution. And I checked it before, so the final solution will be add up to this value. You can check it again because we don't have time, but you can check it. You have to check 6 of the value again, and you will get this result. Okay, so this basically is one of our, and you face this kind of real problem in real world. You face this kind of in real world you can easily measure the slope, you can measure the distance, blah blah blah. So it's easy to do this kind of in order to get the distance between A and B. So this is a practical one, and there's a practical measurement as well. It will look like this one. And once you get this data, we will execute immediately. Of course, depends on whether we can get hold of the machine or not. If you can get a hold of the machine, I execute to do this kind of thing as well, and then you have to measure the distance between A and B straight away. Okay, this is one just for the correction and for the slope and also for the temperature. Now come to the next one, and this one is for the force. Yesterday we stopped somewhere over here, so let's repeat how to continue this one. This is a force. This is a correction for the temperature and correction for the force. So one is more like internal one, and the other one is more like external one. This force is more like external one. So when you put the arrow together, you have to consider, you have to sum it up. You can sum the arrow plus the external arrow, because they are more or less they are independent. So you can just sum them up. If they interact with each other, then it causes some problem. You can't just sum them up. But for this case, it's okay. For the force and the internal and external one, they are sort of independent, pretty much independent. So you can just sum them up. Okay, let's now independently calculate the external force. How are you going to correct? So external force, the question goes like this way. You set out a pack. This is your tape. So you keep on stretching your tape up to some point. So you hold one end of a tape and keep on walking to this point. This is the A point. You put normally the pack. You just insert the pack into the ground, and then you hold the tape up to the point of B. Okay, and but the thing is, if you pull too harder, you will distort the tape to some degree. Not that much, but the thing is, only a little bit will cause some error as well. So we care something small as well. So whatever force you, but in practice, no one really measure his force, how much force he exert on this tape. No one. But you can still estimate In order to pull this one, you can estimate how many newtons I apply on this tape. You can estimate. You don't really need some. Of course, you can use something much more accurate to measure the force you apply from this one. So it's also there are some machine you can measure the force in newtons. How many force you exert on this object. So there is but normally you can do estimation. Let's continue. So now the problem is what? The problem is measured by a tab suspended in the it's called catenary. Catenary is just like a chain. The shape like a chain. So it's a tab is suspended like a chain under a pool. It means this tape might be quite long. For example, if this tape is 5 meters long, then it's easy. It can always be strengthened. It's easy. But if this tape is 15 meters, think about it. If this tape is 15 meters long, then you need a lot of force to pull it straight. So that will cause some error. That's one problem. The other problem is called the sag. So we'll come to the other related problem is called sag. So sag will be like this one. Once you hold this one to the other side, because it's too long, then slightly it will be like a sag. You can see. So it cause problem as well. This will increase increase your nominal distance. So you have to deduct your nominal distance from this speed as well to make as a suppose is a straight one and this is a correct one. So you have to make some correction for a correct. So this is also the catenary as well. Catenary. Okay. So you pull it is 145 newton. 145 newtons. You pull this one. You have to use force in order to get this tape straight. Otherwise, this tape won't go straight. So 145 newton. Okay, one information. And temperature, mean temperature means this temperature is outside the field. So this is field temperature. Get down all the information. Write down the information. Okay, so the mean field temperature is 14 degrees Celsius. Okay, 14 degrees Celsius. Okay, continue. So the length of various segments of tape and different in this tape. So this pretty much is the same like a previous one. You also do the measurements as well. Okay, so you have one section, the other section. But the section will more like this one. You have one section, but it's it's called catenary. So it's like you put a section, you measure this one. It's one section, and then another section. So you do all the measurement a bit like this one. All right. So you have how many span? You have 4 spans. So indeed, you did it 4 times, including this one. You did it 4 times. Maybe you can make it smaller. Okay, you do it 4 times. Also, and each time you just recall. Of course, this a bit inaccurate because they are very close. Okay, so you just recall all the measurement, So the observation, the first one, first span over here is this one. The second one span here, so on and so forth. Okay, let's continue. And so the tape was standardized on the flat. So it means this is a standardized condition. What kind of condition? This is the standard tape. So now you try to define the standard tape. So like I say, there is nothing called standard tape in this word. The standard tape is a concept from a concept. So if you are 2 surveyors doing the surveying, you want to unify their units, but if they measure in different temperature, different pools, then how could you unify the units? So this is one of the approach. You can choose people A and the standardized people A's condition, and then refer people B to people A, and then you can say something in people A's units. Then it's easy to understand. Otherwise, it's hard to understand. So standardized is a relative concept. It's not absolute concept. Like there is something called standardized tape. No, it's just a concept. Okay, so now you standardize this tape based on this condition. The condition is temperature is 18 degrees Celsius. And the force is 95 newtons. This one. So yesterday, like I said, under this force, under this temperature, you pull it. Under this force, under this temperature, if a physical distance, you have a huge physical distance. So this physical distance is called standardized. Of course, you have a nominal tape, the length over here, nominal length over here. So the physical one is this law. This is a nominal one. We call it nominal one. And you call this one the standardized tape. You call this one standardized. So this is a standardized tape. So it being standardized under 95 newtons and 18 degrees Celsius. Okay, one. Now go back. Now you have a temperature is over here. Temperature is 14 degrees. This is our temperature. But in comparison, its temperature is low. So our tape will be shortened. Because it's colder. It will be shortened by physics. It will be shortened. Okay, so it means we if that shorten is we will estimate. So we have deduct the value in comparison. We will deduct the value from the error. So you put you measure this one. Suppose error. So you deduct error is will deduct some value from error to become errors. Okay, that's one thing. So let's calculate the temperature first. Yesterday we briefly mentioned this one. The potential bit. Look at try to find out the thermal expansion coefficient. Where is the thermal expansion coefficient? The thermal expansion coefficient is over where? Over here. This is a linear expansion. It's a thermal expansion. And now he changed the unit. Previously, the unit was using the Fahrenheit. Now you use the Celsius. So if you use the Celsius, you also have to change here this value as well. Suppose they are the same material. If they are some different material, this value of course will be changed individual as well. But so take a look again. Go back. Take a look at this one. This is thermal over here. You see the thermal expansion of the tape material. We don't know the tape material, but this tape material is a thermal expansion is per degree Fahrenheit over here. But now is per degree Celsius. So you have to tear them apart. There is a distinction over here. Okay. Now easy alpha this is your alpha. This is your alpha. The thermal expansion coefficient. This is your alpha. And then now is Tm. Tm is your field temperature over here. I wrote it down already. It's 14 degrees Celsius. So it's 14 over here. T naught is a standardized temperature. It's standardized temperature at 18 degrees Celsius. 18 degrees Celsius. Now L. What's your L? L, of course, he did all the correction at once. You can do it individually. It will be the same. If you do the individual, it will be like this will be separated. If you use my approach, previously I told you the same approach. The reason I use this one is because you have a different angle. So that's the reason I use. Otherwise, in this case, you can use the author's approach straight away. You don't have to spread them into L1 and L2 because it's the same. It will be L1 being corrected times this one, and then plus L2. I better write to be consistent. I better write this way to be consistent with the previous example. I better write this one. So L1 is this one. The nominal measurement meters, and L2 is over here. L3, L4. Okay. So now you want to correct all the correction. You can correct L1 first. So L1 will times all this bit, plus the L2, the L2, and so on and so forth up to in total you have 4 segments for this catenary. So L4 plus L2. So each one of them. So in total, they are this is the value. In total, they are just sum there. Summing up, you will get this value. This is a value. So you don't need to go through bit by bit. And the reason for me to go bit by bit is because this is about slope. That's the reason I take it apart then to make it much more intuitive. Okay, so but in this case you don't have to. I just you can use author's definition. Take this along. So you'll get the CT over here. This is our result. We don't care about this one. We care about the final one, the LOS. So based on this one, how are we going to get LOS? But this LOS is not the final correction. It's just correct the temperature. You still have to correct the false. I will correct temperature first, and then we correct the false secondly. Okay, let's correct the temperature. So how are we going to correct it? Is L first. Then you have to make a judgment. Here is a plus or minus. Of course, you have a CT over here. CT over here. I put absolute value for the CT in order to save my. I don't have to use my brain. I just save it over here. But I still have to use my brain over here, whether it's a plus or minus. But this is easy. Easy. Take a look at this. You need some inference. The standard temperature is 18. We are going to get the value out of the standard temperature, the standard tab. But now we don't have a standard tab. Instead, we have a use tab. Is this one. This is 14 degree, and this is 18 degrees. So this one, the standard one, not standard one, the use tab will be shorter than the standard tab. These are use tab. The one I say is a use tab. This is a standard tab. Easy to understand. Why? Because standard one is 18 degrees. When it's hotter, then the metallic element will be elongated. To some degree, to some bit. Okay, so if you use this one as your tab to do the measurement, you get something longer because your error is over here. So you overestimate in comparison to this one. You overestimate the physical distance. So you overestimate. So you have to deduct it. So I can easily tell this is a nominal one. I have to deduct it over here. So that's the reason I put minus over here. On the contrast, if this is 14, this is 18, then this must be plus. It means you underestimate. Now it's overestimate. You use this tab. If you use this tab, you overestimate the physical distance in comparison to standardized tab. You overestimate. Okay, so far so good. Error. What's the value of it? Error is over here. Error is 100 over here. This is value. Error here. And then minus CT. CT is over here. You put positive and negative. So minus 0.0004. Okay. So in total, you get 119.627 something. You will do the calculation. Just do the calculation. Easy. Okay. This is a temperature. This is a temperature. Shouldn't be a problem in temperature. So far, since there is no problem in the temperature. Now let's take a look at the force. Take a look at the force. Okay. How are we going to correct the error from the force? First of all, let's take a look at the correction for the force. Yesterday we talked about the correction for the force. How to correct the force. And in this case, I have to resort to the I think it's weird. I get to resort to some data I saved. Maybe it's over here. Over here. Okay, so yesterday I sort of like okay, this is what P is poor force. So this is the equation. And also yesterday we told you guys the explanation of this one as well. So this is the explanation. Let's take a look at this one again quickly. Okay. So forget about red one. So CP is a P stands for the poor force. The poor. Okay. And so it's you are going to do the correction. C stands for correction. Are you doing correction? P is your pull, the force you apply exert on this tab at the moment of the measurement. So P is a bit like a mean field temperature at the moment of the measurement. So this is observation over here at the moment. Okay, and P no is your standardized pool. You have to understand. A is your area, the cross section of tape. It means the area of tape. Is easy to understand. E is your Young modulus. And we'll give you all this information. All this one. They have some physical meaning. In order to get this one, but you can understand straight away from this one. If you have a higher P means that you exert much more force. In this case, you have to correct even more. So they are proportional to each other, right? Because you exert too much force, you cause much more distortion. Then in this case, you have to correct even the value must be higher. And also, if you look at error, if you have a longer error, it means you also cause this is nominal distance. So if you have nominal distance, it means you make too much errors. There are too much error content in the nominal distance. So you also become bigger. Look at A. A is your area of the tab. So the area of tab is suppose this is a bigger one. This is a bigger one. If this is a big one, so I think I can draw a picture here. Let me see. Maybe not. I tried last time. I think it doesn't work. Maybe yes. Okay. Suppose you can't draw anything over here. Anyway, so suppose the area is bigger one. Area is bigger one. You pull the force will become less. Here's a less influence on the elongate the tab. If the tab is a thinner one, you pull the force, then the tab will be elongate to much more degree. So easy to understand. So it depends on so it is proportional. If you have the tab is bigger tab. I mean the cross section, the bigger one. Then if less effect on the force exert on this one will less effect because the force being spread out onto the whole bit. If the whole bit is a bigger one, big chunk, if they have a less effect on this one. So it's a disproportional. And as for E, you need some explanation from the physics. So we skip E, but other parameters is easy to understand. So you can take this one as already know. Okay. And so let's take a look at this one. Before that, maybe we have the text short break. And meanwhile, we take let's say 5 minutes break, and then you have to call a roll in the group. So let me just write down just like this one. 1, 2. If you are already here, you are 1, 2, 3. Write your name down over. Treat this as a call roll. So this so write down your name 1, 2, 3. Just in a row, and then I can make sure you are here. Others I don't really believe you are here because now in my screen only 25. So I have to check. I don't want you to just keep on cutting the class, and then in the end you learn nothing, and you try to pass. It's almost impossible. So in order to embarrass each other, so we set up a checkpoint over here. Okay, to read it, and then great. All right, then take 5 minutes break, and then I play music. Meanwhile,